Hi, I'm Maya Steiber, a PhD student from Johns Hopkins University's Intuitive Computing Lab. I'm interested in shaping how we collaborate with robots by using human multimodal responses to robot errors to promote effective human-robot teaming. Through our work that I'm going to introduce today, we formalize the incorporation of social signals in error management with a specific focus on error detection, and also provide resources, including a dataset and an example system, to foster the development of flexible error-aware robotic systems for complex human-robot interaction. Robots will certainly make errors. Robot errors can happen during any task and do not ascribe to our expectations of what could happen. In the context of human-robot interaction, besides the direct impact they can have on safety and task performance, these errors will erode user trust. Their effects vary based on the situation and collaborating individuals. As a result, people will be less willing to work with robots. If not managed appropriately, robot errors' negative effects on an interaction can snowball, requiring more time and effort to recover from them. So we need timely and appropriate error management to effectively maintain trust and mitigate negative effects. Current error management techniques in HRI, when specifically looking at physical interactions, are specially designed for each task and consider a set of predefined anticipated errors, which is only a subset of possible errors made for a task. The resulting methods use two types of inputs: an explicit indicator from users, like users manually reporting an error, and an implicit indicator of robot deviation with respect to a task-specific or domain-specific information. The limitations for these methods is that they do not consider other factors such as teammate values or task context that would affect whether a robot action was an error or its effects on the interaction. So as a result, error management methods are rigid. They are not easily adaptable across people, tasks, and error types. However, as I mentioned before, robot errors are not rigid. They can happen during any task and their effects vary. So providing a robot with enough information about the task and user using these methods to obtain an accurate model of an error and its impacts is difficult across tasks and error types. That being said, the flexibility of errors and its impacts on users necessitates us to have error management methods to be flexible across tasks, people, and error types. So one solution is through the use of social signals. Because robot errors are unexpected, their unexpectedness will likely elicit natural human responses or social signals from their human collaborators. Through these social signals, humans can reflexively and implicitly impart information about the error, tasks, and their own mental model of the robot to the robot. By modeling these social signals, we are informing the robot about the user's perception of the robot's actions, in effect creating a basic second-order mental model. Our prior work has shown that using specifically facial movements in response to robot errors that we can detect errors in real time, and that it has the potential to generalize across tasks, people, and error types. So for error-aware robotic systems, we introduced the idea of a flexible framework to use when designing error management methods that maintains the robustness of traditional methods but improves the flexibility. This flexible error-aware framework takes in 3 layers of input. The first 2 layers are the same as the traditional methods, and I'm adding an implicit input layer of social signals. The addition of this 3rd layer is meant to augment traditional methods and use rich information provided by social signals to allow us to capture unexpectedness and variability in complex human-robot interaction. To gain a more generalized understanding of natural responses to robot errors in physical-based interactions, and to also examine the potential flexibility of our error-aware framework using social signals through the lens of error detection, we compiled a data set from 3 HRI studies. The actual data consisted of calculated facial AUs from videos of these interactions, and the data set is comprised of about a total of 7.5 hours of data, of which 13 minutes are reactions to errors. It was across 73 participants in 3 scenarios, and the data set is open source, available on GitHub. For all of the data, ground truths were determined by 2 independent coders. The dataset had 3 scenarios. The first scenario was contextualized as a human-robot collaboration scenario, where participants actively completed an assembly task alongside a robot run autonomously. The participants and the robot collaboratively built tables, where participants could verbally request pipes and the robots would provide them. There were 2 pre-programmed errors, and the participants could verbally and explicitly report errors anytime during the task. The second scenario was also a human-robot collaboration scenario, but had users work with the robot in a cooking task, where the robots provided ingredients for recipes and the humans would cook them. The third scenario was contextualized as a programming by demonstration task, where users provided kinesthetic demonstrations for the robot to unpack groceries from a bin. The robot then executed those programs, and we inserted pre-programmed errors into the execution. When conducting analysis on our dataset, one of the things we were interested in is the potential social signals could improve on the timeliness of traditional error detection. Looking at interaction sequences, the social signal potential is on average 7.56 seconds. Additionally, our dataset analysis showed that social signals in response to robot errors are fairly widespread and prompt across errors, tasks, and scenarios. For more information about the dataset, please read our paper. I also wanted to offer potential use cases for our dataset. Our dataset could be used as a training dataset for understanding human responses to robot errors. This could be across scenarios or across people. This could be used for flexible robot error detection or just error detection using social signals. Besides error detection, you can use this dataset for error classification. So this could be error type or error context classification for the purpose of generating mitigation and recovery strategies. To illustrate how usable our flexible error framework is, we built an example implementation of an interactive robot system that incorporates all three portions of our proposed error-aware framework: explicit input, implicit domain-specific input, and implicit social signal input. Here is an example. For reference, the user has just requested a green pipe, and the robot drops the pipe as an unexpected error. So what you see here is the robot actively detects an error using the user's social signals, queries the user to confirm that an error has been detected, and then automatically recovers once the error has been acknowledged. So in our work, we present a conceptual error-aware framework that's flexible in human-robot interaction by using social signals, which we have shown to has the potential to improve timeliness of error detection. We also introduced an open source dataset of natural responses to robot errors in physical human-robot interaction and an example real-time implementation of an error-aware framework to promote further research in this area. This work is a step towards flexible, robust error detection, which is key to successful error management. Thank you.